Hello, I'm Martin Thijsens, and on behalf of TAS International, I welcome you to the MADYMO Introduction training, where in the section Initial and Boundary Conditions. The initial conditions in MADYMO can be specified with the keywords starting with the word initial. There's three different keywords. The initial.FE model, which is used to position complete FE models. The initial.part, which is used to position only a part of an FE model. And the initial.node.disp and node.val to position individual nodes of the FE model. The initial.FE model defines the initial position and or velocity and orientation of a complete FE model. Note that as a user, you can specify the initial position with respect to the reference space or with respect to a certain body. Note that the initial condition, the initial position, can also be specified with respect to the zero, to the origin of the FE model, or with respect to a specific chosen reference node. The initial.part works in pretty much the same way, where position and orientation are defined, and again the positioning can be done with respect to the reference coordinate system or a body local coordinate system, and with respect to the origin of the model or a specific reference node. Note that when you combine the initial.FE model and initial.part, the order in which both are applied is first positioning of the entire FE model and then repositioning of the part. The kinematic boundary conditions in MADYMO can be specified with an abundance of keywords, most notably the support, which supports nodes to the reference space or a body, the keywords state.FE model and rigid elements, which make parts of FE models rigid, as well as motion prescription, type surfaces, and others. Here we will limit ourselves to the first couple of keywords. The first kinematic constraint is the support, which fixes a node either to the reference space or to a rigid body, and where the user can specify to specifically fix certain degrees of freedom or all degrees of freedom to the reference space or body. Note that when the node is attached to the rigid body, the mass of the node can be transferred to the body with the update body inertia keyword set to on. The next kinematic constraint is the state.FE model, which is a switch which is used to make a complete FE model rigid or flexible. Note that when it's switched to rigid, all nodes are supported to either a body or to the reference space. The state.FE model keyword is generally used to speed up a calculation in intervals of the simulation where the FE model is not yet supposed to deform. Similarly, the rigid element keyword can be used to make a specific element or group of elements rigid. Note that when a rigid element is specified, the user has the option to add additional mass or additional inertia and to apply a linear or angular velocity. Next, we will give some details on the motion keyword. There's two groups of motion keywords. One is prescribing the motion or velocity of nodes, and the other one, detailed in the next slide, is the motion keyword that describes the motion of an entire FE structure. The motion.node.disp or node.val keyword is used to specify a uniform motion of a nodal set, meaning that in the list of nodes that are included under this keyword, the functions for displacements in x, y, and z direction and rotations are applied uniformly to the entire node set. The motion.struct_disp or struct_val keyword is used to prescribe the motion of an entire FE model, but this motion is not necessarily uniform. The motion generally stems from a previous finite element calculation, either in MADYMO or in an external FE code, as illustrated in this slide. For example, where the user has done a finite element calculation with the finite element package LSDyna, where the 3D plot file is loaded into MADPost, exported to a prescribed structural motion file, and subsequently read back into MADYMO to do finite element-like calculations, but without the calculational overhead. This way, simulations, for example in side impact, where the motion of the door or the entire side of the car is important and interacts with the occupant. Similarly, prescribed structural motion can be used to study the effect of footwell deformation on the occupant in frontal collisions. The tight surface keyword is the last kinematic constraint that we will detail here. The tight surface element is there in two forms, the brake force and brake stress, where both indicate that failure of the tying is done either on a force-based level or a stress-based criterion. Note that the nodes are tied to the finite elements in a mesh-independent fashion, and that each node-element combination can fail independently. Post-failure behavior can be modeled by specifying the energies after the rupture event, similar to what is done for interface elements. Then the dynamic boundary conditions. Dynamic boundary conditions in MADYMO can be specified with the support restraint element, the load elements, and through contacts. The support restraint element is a force-based connection between a rigid body or the reference space and a node. Note that the support restraint keyword only works on translational degrees of freedom. Generally, that is enough when enough nodes are connected to a, for example, rigid body. The stiffness of the restraint is automatically calculated or can be specified by the user through a characteristic. The support restraint keyword is generally used in coupling calculations to couple external finite element nodes to MADYMO rigid bodies. The load keyword can be used to load individual nodes, element edges, or element surfaces by a specific load. Furthermore, elements or complete systems can be loaded by an external gravity field through the element occ and system occ keywords. This wraps up our demonstration of the initial and the boundary conditions of MADYMO. Thank you very much for your attention.